Hey guys, welcome to the video. Today we're going to talk about the introduction to limits and how to evaluate it analytically and graphically. So, to define the limits at the beginning, we're going to say it's going to be approaching a value that we're not going to necessarily reach it. And the real-time example would be hitting a brake paddle in a car and the speed is decreasing to 0. But necessarily it's not, because the car hasn't stopped yet, but we do know that it's going to stop at one point. So to start with this function, we're going to get x squared minus 9 over x minus 3 as the limit of x is approaching to 3. So at first we could just directly substitute the 3 and we're going to see that it's going to be 3 squared minus 9 over over 3 minus 3, which is going to be 0 over 0. And the answer is going to be undefined. So to do this in another way to find a definable answer, we're going to see that if we could substitute a value that is close to 3 and if there's any possible way that we could get a definable answer. So we're going to start with the 2.9, which is close to 3, and if we directly substitute the value, we're going to get 2.9 squared minus 9 over 2.9 minus 3, which is going to be 5.9. If you just put the number directly to a calculator, you could see it. So we're going to get 5.9, and to get a closer value to 3, we're going to do 299, which is going to be, I'm just going to write that fast, but you could do it by yourself. It's going to be 5.99 for 3.1 if we want to just get close to the 3 from the right side, which is so this is the right side and this is the left side. If you don't know, we're going to get soon into the definition of the left side and the right side in the video, but for this one we're going to get 6.1 and 6.01. So the more closer we get, we're going to get closer to the number 6, and we're going to see that the limit of this function is going to be 6. But other solution that we could use is find a way to cancel the denominator to get rid of the undefined answer. And that's by opening up the x squared minus 9, which we're going to see that the conjugate of x minus 3 is going to be x plus 3. And if we FOIL these two together, we're going to see that it's going to be x squared minus 9. And we could cancel these two together. So the limit is going to be x plus 3 as x approaches to 3, and the final answer is going to be 6. And to draw this, graph this, we're going to see that it's going to be the x function that we know it's going to be something like this. I'm sorry. Let me just make it more. Yeah. It's going to be something like this. And if we want to just shift it higher by 3, we're going to get to this. Oh no, come on. Yeah. So this is the graph of x plus 3, which is x squared minus 9 over x minus 3. And the limit of it, it's 6. So here's another example just to make it more sense for you guys. And it's a complex fraction. So if we want to substitute directly the value 0 to the function, we're going to see that the answer is going to be another time undefined. So we need to find a way to cancel the denominator somehow to just get rid of the 0, or just multiply the fractions together to see where it goes. To just start, we're going to see that the numerator fraction is actually a bit extra from the first part, and we could rewrite the x squared plus 4x over x plus 4 and cancel the denominator. And for the second part, we're gonna just write the same thing, and the denominator is gonna be still 0, which still is gonna be undefined, but so we're just gonna get rid of the 4's, and we're gonna see that the limit is gonna be x over x as x approaches to 0, and the answer is gonna be 1 as we cancel out the x's. So for the next example, we're going to see the limit of square root of x minus 2 over x minus 4 as the limit x, as the x approaches to 4. And the answer is going to be yet 0 over 0, which is going to be undefined. So if we could find a way just to rewrite x minus 4, we could see that. Let me just first write a formula. I think you guys mostly might know this, but just in case, if you don't know or just want to remember, or as a reminder, we could rewrite the denominator as square root of x minus 2 by its conjugate, which is going to be square root of x plus 2, and the numerator is going to be x minus 2, which we could see that we could cancel these two. This one is going to be 1 over square root of x plus 2 as x approaches to 2. And the answer is going to be, let me just write it down here. I'm sorry, this is 4. It's going to be 1 over square root of 4 plus 2, which is going to be 1 over 4. But for this example, sometimes the direct substitution is just going to work well and there's nothing complex. And it's usually for the limits that it's not going to have a denominator and it's going to be simple like this. And if we just directly substitute the value 5 in the limit of x squared plus 3x minus 8 as x approaches 5, we're going to see that this thing is just going to work without a problem, and the limit is going to be right here. Hold on. Going to be 32. Well, for the last one and the big one, It might seem a bit complex, but we need to rewrite the numerator the way that it could cancel with the denominators. Right now it's 0 over 0, and it's undefined. So for start, if we check this formula that it's written down below, we could see the a plus b cubed or a minus b cubed is a cubed plus 3 times a squared times b plus 3 times a b squared plus b cubed, or for the subtraction it's going to be the b cubed is going to be negative, and the 3 times a squared b is going to be also negative. So if we try to find a way to rewrite the denominator like that, we're just going to check if the cube root of x cubed, it's going to be x, and the cube root of minus 64 is going to be also minus 4. So if we rewrite this to see if it's correct, you could also just forget the formula and just open it up and 3 times and try to FOIL it to see whether it goes the same way or not. So it's going to be x cubed minus 3 times x squared times 4 plus 3 times 4 squared times x minus 4 squared and 4 cubed, So it's going to be, this is going to be minus 64. That's going to be 16x2. 16 times 3 is going to be 48, and this one is going to be minus 12x squared. So we could see it's the same thing with the numerator, and we're just going to rewrite it like that. For this one, it's going to be x minus 4 cubed over x minus 4 multiplied by square root of x minus 2. And we're going to cancel these one for now. And it's going to be x minus 4 squared. So if we check and multiply the square root of x by its conjugate, square root of x minus 2 by its conjugate, we're going to reach to x minus 2. And for that, open up the numerator. And I'm going to get something like this over square root of x minus 2. And if we check this out, this is going to be x minus 4, and this is also going to be the, hold on, let me check it out. All right, so this one should be x minus 4. And this is going to be the same with this. So if we cancel these two and directly substitute the 4, we're going to get 0 times the square root of 4 is going to be 2. It's going to be 0 times 4. And the limit of 0 times 4 as x approaches to 4, it's going to be 0. So in this part, we're going to learn how to evaluate the limits graphically. So starting from the left side, if we see and check that how the function is going from a certain point from the left side and the right side, and it's closer to which value. If the left side and the right side are these similar, the limit does exist, and other than that, it does not exist. So for example, if I want to see that the limit of this function as of x approaches to -3 from the right side, we're going to see slightly from this part that it gets close to 2. So the limit of this function from -3 from the right side is going to be 2. And if we look from the left side also, as x approaches to -3 from the left side, as we look slightly, it's getting closer also to 2. So if a limit from a left side and a right side are similar, it means that the limit of that point from the both sides are the same, which means the limit of this function when x approaches to -3 is 2. Also, feel free to pause the video anytime just to help yourself and see how could you solve it by yourself too. And right now we're going to check out the limit from the -1. As we can see, we do have a vertical asymptote, which is a red line right here. And it shows us that from the certain sides, one or both the function is getting to an infinite point, whether if it's positive or negative. So at this point, if we want to check the limit as x approaches to -1 from the left side, we could see that it's getting to -infinite, and also from the right side, it's also getting -infinite, which means that the limit of this function as x approaches to -1 is -infinite. And for this part, we're going to check if the limit is available or not, and if yes, what are the values. So for the x equals 1, if we check the limit from the left side, we're going to see that it's getting close to 3. And when it's getting the limit of this function, when it's getting as x approaches to 1 from the right side, 1 from the left side, and this is the right side, my bad. From 1 from the left side, it's getting closely to 1. So it means that these limits, as we can see, are not equal, which means the limit of this function as x approaches to 1 does not exist. And okay, for the second function, I wanted to give you this as an exercise, so feel free to ask any questions if you got any problem, but just wanted to just point out something real quick about the discontinuities. And discontinuities are when a function is not connected graphically and there's a gap by either a jump or a hole. And let me explain it how it's just going to happen. So as we could see from the open interval of 1 and 3, we do not have any discontinuity and the function is slightly connected. So it's continuity. But if we reach a level which there's a big gap, we're going to call this a discontinuity. And this type of discontinuity, when there's a gap and the value changes at like a same point, we're going to say this is a jump discontinuity. But for other specific examples like this, we could see there's also a discontinuity from the open interval of negative infinite to, let me check this, -1, actually closed interval. There's a tiny discontinuity, and that's a whole discontinuity, if we could see right here. And this is called, as we said, a whole discontinuity. And a whole discontinuity is removable, and since we could just get a value out of it, just a specific point, but points like this and discontinuity, jump discontinuity, is unremovable. As we could see, there's a big gap and the function kinda disconnects. So that's it for this video. Hope you guys enjoyed it. Feel free to ask any questions from the comments. Don't forget to like and subscribe, and take care.